Okay, good day to each and every one of you. This will be part 2 in solving this given beam that we have. Since we're done with part 1, let's proceed to part 2. And we are going to be concerned with segment B-C for this video. So upon doing that, let's get it right on it. And all we need to do is to consolidate the free body diagram of B-C included A-B. By doing that, it should be like this. This is the beam. This is the section we cut. Let's say this is point F, and this one is the shear force going downward. And this one is the bending moment rotating counterclockwise. And for this point A, this is 200 pounds. At point B, we have here a reaction equivalent to 880, and the new uniformly distributed load, okay, going downward, goes like this. So you can see here, this is the given uniformly distributed load having a definite length equivalent to 10 feet. Since we did a sectioning, we are only going to consider this portion of the uniformly distributed load, okay, because we are concerned only on the left side. And upon doing that, this should be 120 having the new length, which is this one from point B to point F. If this one, the measurement for this is 4 feet, and the whole measurement of this whole beam is equivalent to x, means to say that the length from B to F, that should be x minus 4, right? So now we have each measurements for each points, A to B, B to F. And in order for us to simplify this uniformly distributed load, we must first get the concentrated load of this one. Because the length of this uniformly distributed load is x minus 4 and the magnitude is 120. Means to say that the concentrated load acting here at the centroid of this rectangular shaped object, that should be 120 multiplied by the length, which is x minus 4. Okay, so we need to solve for V by summating all of the forces along the y-axis is equals to 0. So that should be negative V. We have this concentrated load going downward, so that should be negative 120 x minus 4. We have this positive 880, and we have negative 200. So simplifying this, all we need to do is to transpose V to the other side. So that should be, for that shear formula, simply 880 minus 200 minus 120 x minus 4. So if we're going to simplify this one, simple algebra is equals to 1160 minus 120 x, and don't forget about the unit pounds. So this will be the working formula for the shear load at segment B-C. Okay, all we need to do next is to solve for M. Okay, so in order to solve for M, we just need to use the summation of moments. So where are we going to settle our pivot point? At point F, where we managed to cut our beam. So summation of moments rotating counterclockwise is positive at point F is equals to 0. So what are those forces that tends to rotate our structure? We have this 200 pounds going to rotate counterclockwise, so that should be positive 200. The perpendicular distance is x. Okay, that should be x. And this 880 going to rotate the structure clockwise, so that should be negative 880 multiplied by the perpendicular distance, which is x minus 4. And last but not the least, this concentrated load 120 x minus 4, so minus 120 x minus 4, and the perpendicular distance is simply half of this x minus 4. Okay, so x minus 4 divided by 2 plus m, which is this one. So all we need to do is to simplify. This one should be 200x, and this one should be simplifying 880x, and 4 multiplied by 880, both negative, so the answer should be positive 3520. 3520. And this one, you just need to simply simplify these two polynomials, and then 120 divided by 2. So that should be, don't forget that the rotation of this 120 multiplied by x minus 4 is counterclockwise, so that should be positive, okay? So plus, don't forget about the sign of 120. So that should be positive 60, x minus 4, and then x minus 4 plus m. Okay? So from here on, all you need to do is to simplify this one, this polynomial. So upon doing that, this is just simple algebra. The result should be transpose everything to the left side so that m would be the one remaining, and then rearrange everything. So m is equals to negative 60 x squared plus 1160 x minus 4480. Then don't forget the unit for the bending moment. That should be pound foot. Okay. So we managed to solve for the shear equation at segment B-C and the bending moment equation here for segment B-C equivalent to this one. Okay, so this one is really important, so you should never forget about that. And since we managed to solve for, or rather look for the formulas for the shear and bending moments in our beam, the next step is to use approximation. Okay, so I'm going to free this whiteboard here so that we can have some space for us to solve. So don't forget about the equations that we managed so far to solve, and all of those informations will be important for solving this problem. Okay, so upon doing that, the next step here is to list down all of the shear and bending formulas that we managed to solve. So this one is for segment A-B. So for segment A-B, the formula for V was simply, we have an exact answer, negative 200 pounds. And for M, that was simply negative 200x, okay, pound foot. And for segment B-C, okay, the shear formula was basically V is equals to 1160 minus 120x, and for the bending moment, that was negative 60 x squared plus 1160 x minus 4480. Okay, so these are the shear and bending formulas for segment A to B and then B to C. And the next step that we are going to do here is to use approximation. And what are those limits that we're going to use? Well, obviously, we're going to start at segment A-B. Okay, A-B, we're going to start here at A-B. So upon doing that, so for segment A-B, we need to somewhat get this length x to a certain value, and that value should be from this point A all the way to this portion of the beam. So we're going to use here approximation. So upon doing that, all we need to do is to assume that the value of x, okay, the value of x is greater than 0 but less than 4 feet. Okay, less than 4 feet, because we are approximating here the value of x. So upon doing that, let's go back here to the formula of the bending moment at segment A-B. So that should be negative 200 multiplied by x. Let's start by 0. So obviously, the answer for this one is 0 pound-foot. And if we're going to substitute x by 4, so that should be negative 200 multiplied by 4. The answer should be negative 800 pound-foot, right? So we have this value. Let's say this is number 1. Let us proceed to segment B-C. Okay, B-C. Let's start here by V. 1160 minus 120. And don't forget that the approximation for x for segment B-C should be x is greater than 4 but less than 14 feet, because we are already done with segment A-B, so we're done with that one. We are concerned with from this portion, okay, from this portion all the way to this portion, okay. So that's why we are setting up the limits of our x by 4, okay, by 4, which is this one, and the whole length of the beam, which is 14, because 10 plus 4 is 14, okay. We are only approximating it here, guys, okay, don't forget about that. This one. So replacing x by 4, so v is equals, if we're going to simplify this one, we should have an answer equivalent to about negative 680 pounds, okay. So let's say this is number 2, and let's try to replace by 14. So v is equals to 1160 minus 120 multiplied by 14. So v should be equals to negative 520 pounds. So that should be number 3. Don't forget about that. That's important. Okay. So now we have the values for the shear load for A-B, which is 200 pounds, and for B-C, which is, if we're going to replace x by 4, that is negative 680 pounds, and if we're going to replace x by 14, that should be negative 520 pounds. This is really important because we are going to need this information for graphing the shear and bending moment diagrams later on. So let's proceed by solving the bending moments for segment B-C. I'm just going to remove this one because we're already done with that. Upon removing this one, the next step, so M, we're going to use this one by replacing x by 4. So M is equals to negative 64 squared plus 1160 multiplied by 4 and minus 4,480. So M should be equivalent to negative 800. Okay, negative 800 pound-foot. Negative 800 pound-foot. Don't forget about that. And the next step that we are going to do is to replace x by 14. Okay, I'm going to remove this. So upon doing that, replacing x by 14, so negative 60 multiplied by 14 squared plus 1160 multiplied by 14 minus 4,480. So M should be approximately negative 11760 plus, I think this is approximately 16,240. 16,240 minus 4480. The answer for this one should go back to 0. Okay, and that's it for the part 2 of our discussion. And of course, we're going to proceed with part 3 after this lecture.